Hi everyone, thank you for joining us. I'm going to hand you over to Killian in a second, who's a PhD at Biometris, working on the incorporation of high throughput phenotyping data and incorporating them into mixed models for G/E interactions. I had the pleasure of seeing one of Killian's talks at PAG back in January, so I can safely say we're all in for an absolute treat today. And with that, I'm going to hand over to you, and yeah, looking forward to it. Thanks, Killian.
Yeah, thank you for the introduction. Today I'll indeed be talking about some of the work that I've been doing for the past few months, which is indeed based around mixed models for genomic prediction and G/E, mainly using ASReml. So I'm going to be talking about, let's say, including environmental covariables in these mixed models to get better predictions for the G/E. Just as a bit of an overview, I'll start with an introduction, just sort of to reiterate the basic concepts of genomic prediction and G/E, as well as genotype by environment by management interaction. Then I'll give a short introduction on ASReml's own function, which is actually what I've been using mainly to model the G/E. I'll talk a bit about Enviromics and environmental covariables. Why would you want to use those for G/E? And then we'll move on to, let's say, 4 models that I've been working on using kernels, which are essentially sort of kinship matrices for the environments based on covariables. And I'll talk about linear forms of those as well as nonlinear forms. Then I'll have a quick note on modeling multi-trait data. So instead of modeling genotype by environment by management, we'll be looking at genotype by environment for multiple traits. I'll show just a few results that I've had so far, and then I'll make a note on code availability. So let's say if you want to try it yourself, if you maybe want to adapt it to your specific use case, you'll be able to essentially use the code as well. So if that, I'll start with the introduction. Like I said, my work mainly focuses on genomic prediction. So just to reiterate the basic concepts, I think the easiest form of genomic prediction would be a simple G-blood model, which in the case of a linear mixed model would look something like this, with a vector of response variables, whatever trait we're interested in predicting, a design matrix for the fixed effects, as well as a vector where we get the blues for those fixed effects. Similarly, for the random effect, we have a design matrix that links, let's say, records to genotypes. We've got the blobs for the genotypes in U, and then, of course, some sort of residual. And U and epsilon being random effects, of course, have some sort of distribution centered on 0, and with covariance matrices that involve let's say, genetic variance, residual variance, and then something to structure those. So typically, of course, residuals, we think of them as independent, and for the genotypes, we can use a pedigree-based relationship matrix or a genomic, let's say, SNP marker-based kinship, and that's what I'll be using today. So for the remainder, I'll be using K for that kinship. Of course, GBLUP is for a single environment. So if we're looking at a single trial and we want to do prediction within that trial, as soon as you move to multiple environments, you are going to have to start dealing with something called G/E, genotype by environment interaction, which is something that's caused by genotype-specific adaptability, right? So some varieties may see a big performance increase if they are being grown in a better environment, whereas others might be more stable, and you won't see any kind of slope moving from from worse to better environments. So on the right, you can see sort of just a kind of graphical representation of this. Both forms are actually G/E. On the top, we have crossover interaction, where the ranking of the varieties or genotypes changes depending on the environment. On the bottom, we don't actually have a change in ranking, but there is, let's say, heterogeneity of variance. So the differences between the genotypes are going to be larger in environment 2. And those are both forms of G/E that you, ideally want to model and keep in mind when you get predictions for genotypes in specific environments. So if you want to do that in a mixed model, it's a fairly simple extension. I mean, mathematically, the model looks the same. The only thing that changes is the covariance matrices for the random effects. So for epsilon just becomes bigger, but typically we still assume that they're all independent with maybe a single variance. For the genetic part, we have the kinship, but we now have this Kronecker product with some sort of covariance matrix that describes the correlations between environments, genetic correlations, which, if they're very high, there's little G by E. If they're close to zero, there's, a lot of G by E, a lot of crossover interaction. K is, well, normally known, of course, given the SNP markers, and sigma E is something that we would have to estimate using maybe an unstructured model, factor analytic, compound symmetry, different structures that have different numbers of parameters. If we then want to, let's say, look at multiple environments, but also multiple managements, let's say, 10 environments with 2 different nitrogen application rates, we can, intuitively make that, do that quite simply by just adding another Kronecker product and another covariance matrix for the management. So let's say that we have 2 managements. This would be some 2 by 2 covariance matrix, and then we have something for the environments, and then finally the kinship for the genotypes. You could do that with, let's say, a general correlation matrix for the environments, and then an unstructured covariance matrix for the managements. But in my experience, that's quite hard to fit, let's say, directly in ASReml as this sort of double Kronecker product. So I think what a lot of people actually end up doing in practice is they end up fitting, well, essentially the same model, but combining the management and the environment factors into a single new factor, which then, as the levels, contains all of the possible combinations of management and environment. And then that structure, of course, can be modeled using an unstructured model, factor analytic, etc. Also note that for all of these models, we could in principle use multiple residual variances, one for each environment, for example. That doesn't necessarily have to do with the covariance model for you, but it's just something to keep in mind. Also, the models that I'll be talking about later, the examples that I'll show use a single residual variance, but it's perfectly fine to use multiple residual variances there as well. And one final note, because I'll be talking about G by E by M as well as multi-trait G by E, so to speak, or genotype-by-environment by trait models. If you have multi-trait data, let's say plant height and grain yield, traits that are measured on the same plants also mean that you need to keep residual covariances in mind. So in that case, the distribution for these residuals would be a little bit more complicated and also involve some sort of covariance matrix that we need to estimate. So just as a summary, if you think of it graphically, if you fit the model using this double Kronecker product, you would have some, well, usually, the genotypes, you would have the largest number, so you would have a big kinship describing the correlations or the relationships between the genotypes. We've got some structure for the environments that we need to estimate, and then we've got usually, a few managements or a few traits that we also need to estimate a covariance structure for. So, with that in mind, the basics of, let's say, genomic prediction for multiple environments and management, I want to talk about ASReml's own function, which is the thing that I've actually been using to fit these models with kernels. This is a small, let's say, subsection of the documentation. The full documentation you can find on the VSNI website at the link below. But own essentially allows you to specify an external function in your R environment that provides a covariance matrix or its inverse, and also the derivative matrices of that covariance matrix with respect to parameters that you can actually sort of choose yourself. So the nice thing is that with the built-in functions like core GH or US or FA, you're bound to the structure that's programmed in there. But here you can actually sort of program your own structure, your own parameterization, meaning you can fit, for example, nonlinear kernel models, which I'll get back to later. So within ASReml, you use it like this. In the call for fitting the model, object would be, let's say, the name of the factor in your data frame that you want to model using this covariance structure. Fun would be the name of this external function. And then we also need initial values for all of the parameters. We need to specify types, so whether they are variances or correlations. And optionally, you can also specify constraints. So variance, of course, can only be positive. If, again, you think about it graphically, this is kind of what's happening if you use this own function. So we have the call to fit a model up here. Of course, this all relates to the random part because we're modeling it using a covariance structure. essentially what you get is if you fit a model like this, at every iteration, ASReml is going to come up with values for the parameters that you specified yourself. Those parameter estimates at any iteration are passed to the external variance function, and this thing you can program yourself, but it needs to have two arguments and only these two arguments. Order, which is simply going to be the number of levels in the vector that you want to model. So if you're looking at environments, it would simply be the number of environments. And kappa, which is actually going to be, let's say, a numeric vector containing those parameter estimates. That function, which you program yourself, then computes the covariance matrix and all of the partial derivatives with respect to those parameters and passes that back to ASReml, which ASReml then uses to update the estimates, and then the whole circle starts over again. So just as a sort of simple example, I wanted to basically use own to fit an unstructured G/E model, just to get an idea of how it works. Using a subset of drops data, which is data from a European project. For the small example that I'll show here, it's just one trait, grain yield, very simple, 3 rain-fed trials in Europe, 246 maize genotypes, and a kinship based on genomic markers. And so we'll see how to fit, let's say, an unstructured model for those 3 environments using both the built-in function core-gh as well as own. So just to, recap an unstructured model, I think most people are familiar with it, but it's essentially a completely free model, right? So you've got variances on the diagonal, a variance for each environment, and then you've got the correlations between each pair of environments. So if you think back about the slide on the own function, our vector kappa is going to look something like this. We've got the correlations first, and then the variances. So I'll just switch to my RStudio now and show you how you would actually use that in R. I'll start with loading ASReml, of course. Just load in some data as well as the kinship, and then we can actually take a quick look at the data just to get an idea. Like I said, we've just got 3 trials. We've got 246 genotypes, and the phenotypic data looks something like this. So we've got differences in means and also, maybe a larger variance for the third environment. Do note that these are, phenotypic data, so these things don't necessarily say something about the genetics, but it's good to get some kind of idea. If we start plotting the grain yields for different environments against each other, we can take a quick look at the G/E. Here there seems to be a pretty good correlation. This one's probably going to be close to 0, and then the final one is actually probably the highest correlation of all of them. So here I fit the model using core-gh. I don't fit an overall intercept, just take a fixed effect for all 3 environments, an unstructured model for the environments, known relationship matrix for the genotypes. And then if we look at the variance components, we indeed see the 3 correlations. 2 of those are fairly decent, and indeed the one in the middle is close to 0. And also if we look at the variances, we've got 2 relatively low variances and 1 that's a bit higher. So that seems to match the data quite well. Then I'd like to fit the same thing using the own structure. Given the amount of time today, I won't go into the code and show exactly how it's computed, but the idea is that, like I said, you assume a sort of order for kappa. So in this case, I'm just going to say that the first 3 elements of kappa are going to be the correlations, and the final 3 are going to be the variances. Well, then we can define this variance function, and just to quickly sort of show how it works, this part essentially computes the covariance matrix. Here we compute the derivatives with respect to the variances, and then finally the derivatives with respect to the correlations. And we pass all of those back to ASReml in one big list, starting with the covariance matrix, and then the derivatives in the same order as how we sort of specified it. We don't explicitly specify it, but the way that we build these matrices kind of specifies it anyway. But it's important that they are in the same order. Well, then we need initial values, types, and constraints. Initial values, in my experience, you can just pick 0.1 for everything. For the types, we've got 3 correlations and then 3 variances. Correlations can be unconstrained, and variances, of course, should be positive. Then we fit the exact same model, except that we now use own here in terms of core-gh. And then if we look at the, for example, log likelihood of both models, we see that they are indeed the same. If we look at the variance components, yeah, it's a bit hard to see, but those are identical as well. We can just use the all equal function to check if they really are equal, which they are, so that's good news. That means we didn't make any mistakes. I mean, you wouldn't really use this for an unstructured model, of course, because you have the built-in functions, which are, well, way easier to use and probably also faster. But I think it's a good way of sort of understanding how to use this own function. Then let's go back to the slides. So that's just yeah, like I said, a sort of simple illustration of how to use this own function. And then I want to move on to, well, some actual Enviromics and using these kernels. So Enviromics is, let's say, similar to genomics or phenomics in the sense that you, with genomics, you use genomic data markers. Phenomics, you want to use, extra phenotypic data from drones or whatever. And in Enviromics, you typically want to use environmental covariables to model the G by E. Well, why would you want to do that? I mean, the environmental covariables probably say something about the weather or the actual environment that plants were grown in. So the idea is that they must also be useful to model the actual G by E. And I think there's two settings that are where they are especially useful, and that's prediction into new environments, because we don't have any phenotypic data there. We might be able to, have some idea of the G by E using those environmental variables. And I found that they're also actually quite useful if there's limited overlap between environments in terms of genotypes. So I think that's something often referred to as sparse testing. You can kind of see it graphically here on the right. So let's say that we've got our genotypes on the y-axis, environments on the x-axis. What you then have with sparse testing is you have, let's say, a small number of genotypes that are tested in all environments, and then the remaining genotypes are tested in the most extreme case, in only one of the 4 environments, in this case, or perhaps, in 2 of the 4. So there's, let's say, partial overlap, but there is a lot of missing G by E combinations. I think that happens quite a lot when you have data sets of multiple years, where the population changes between years. Yeah, or perhaps just, trials within a year as well. And of course, it also means that you can test quite a lot of genotypes, quite a lot of environments without needing to evaluate, the full number of plots in the field. So yeah, we want to use environmental covariables for that. Are there other ways next to these kernels? Yes, there are. I think random regression is a sort of well-known example. Reaction norm models is a term that's used a lot as well. I think, to be honest, these reaction norm models and kernel-based models are more or less the same thing, in the sense that they both use the environmental covariables to, well, kind of construct a kinship of your environments, basically. But instead of using genomic markers like you would for the genotypes, you use, well, environmental markers for the environments. So I now want to start with let's say, the 4 models that I've been looking at. They all use kernels, and how I get to 4 of them is by looking at linear and nonlinear kernels and combining these 2 with, let's say, 2 options for the variances. But we'll see that as we go through here. So let's just recall the sort of, basic form of the genotype-by-environment-by-management mixed model. If we wanted to use this double Kronecker product, it would look like this. So we have a kinship for the genotypes, some structure for the environments, and some structure for the managements. The management structure is something that we actually want to estimate. The environment structure is something that we could estimate from the phenotypic data. But instead of doing that, we now want to use a linear kernel based on the environmental covariables. So how do we get this linear kernel? Well, let's assume, or let's think that we have a matrix W, which contains in the rows environmental covariables related to, I don't know, temperature, radiation, moisture, water availability, etc. And in the columns we have, let's say, Q environments for which we have those data. Well, they need to be column-wise scaled and centered, and then we can actually take the transpose of that matrix, multiply by itself, and then divide by W minus 1, which would be the number of environmental covariables minus 1. And this is actually, well, this would give us our linear kernel, let's call it C, which we would then use in place of this, covariance structure that we maybe would have to estimate from the data. Well, what that means is that a linear kernel is, to be honest, just a fancy word for a correlation matrix, because that's all that we're doing. We're computing a correlation matrix of the environments using the environmental covariables as, well, sort of predictors, basically. And then we want to put that into our mixed model. So yeah, like I said, we want to combine it with, in this case, an unstructured model for the management, because typically you have a relatively small number of managements. In the example that I'll show today, it's only 2. So in that case, an unstructured model is perfectly fine. Want to combine it with the linear kernel for the environment C. And then, like I mentioned before, we have 2 options. So we can either assume that all environments within a particular level of management are going to have the same genetic variance. Or we can assume that we can make the choice to model a unique variance, a unique additive genetic variance for every environment by management combination, which, I don't know, may be interesting from a prediction point of view, especially if we think about errors. Because, I mean, having unique variances here also implies that we get different rates of shrinkage, which perhaps gets us closer to the values that we actually want to predict. The first one would be a model that uses the linear kernel with a single variance for all environments within a level of management. Mathematically, I guess it would look like this. And we would have our vector kappa, which has a variance for the first level of management, a variance for the second level of management, and a correlation for a correlation between the 2 levels of management. So again, this is assuming that we have a data set with, let's say, low and high nitrogen, or rain-fed versus irrigated trials. We estimate that red matrix, and then we plug in the linear kernel and the kinship, and that should give us our model. I've written it out here just to, I've not done that for all models, but I've just written it out here to get an idea of what it would look like. I mean, in principle, it's fairly simple. We've got the unstructured covariance matrix here in red, because it refers to the management. And then we've got our known linear kernel in green here. Take the Kronecker product of these 2, and then we get the full sort of covariance matrix of the environment by management part of our full structure. The kinship, of course, comes after as well, but I mean, we don't necessarily do anything with the kinship here, except that we use it to model the genotypes. So if we think back to the own function, we needed to specify an external variance function that returns the covariance matrix, which would be this thing, and it needs to return the derivatives as well. So just to give one example, if we take that covariance matrix on the last slide, and we want the derivative with respect to the first variance, it's simply looking at which elements, let's say, depend on V1, and then computing the derivatives with the normal rules. So, I mean, in the bottom right corner, we don't have V1, so those are going to be 0, and the other ones are going to be, some derivative. We also need to compute the derivative for, with respect to V2, and also with respect to the correlation between management 1 and management 2. So before moving on to the next one, maybe I'll just show that in our studio again, how you would do that. So, we load in ASReml again. We load ggplot because I want to make a few plots. We'll load in some data, and I'm going to make it, so this is the drops data. I'm just going to make it a little bit smaller. We'll look at 4 environments, make a few extra factors for fitting the models, load in the kinship, and then here we load in the, let's say, linear kernel, and I'll load in the nonlinear kernel as well, but we'll get back to that later. This is actually quite important if you want to use this, because, I mean, ASReml doesn't have any idea on which column of your linear kernel corresponds to which environment. The only thing that it has is the order of the levels of the environment factor in the data frame that you pass to ASReml. So we need to make sure that those kernels have the same ordering as those levels. We can plot the data again just to get a quick look. So we've got indeed 4 environments, 2 managements, the rain-fed trials, because R is rain-fed, W is well-watered, I believe, so irrigated. Interestingly, the rain-fed trials actually seem to have slightly higher yield here. Here there's a big gap, and the well-watered trial is better, and then here there's a small gap. In terms of variances, they all seem to be more or less similar. Then we can look at the genotype by management interaction by plotting, let's say, grain yield for the same environment, but different managements. So we can do that here. Well, it's pretty good correlation, so probably little interaction. Well, this one's even better, so to speak. This one does seem to be pretty close to 0, and the final one is pretty good as well. Then for the G by E, we can do something similar. We can just take the same management but different environments and plot those values against each other. Which, well, there's quite a lot of G by E here. And if we look at card 12 versus card 13, I believe, so that's the same location, Karlsruhe, I think, in 2 different years. There's, well, let's say a very high correlation between them, which is not something that is completely unexpected, I think. Then we'll fit the, let's say, single variance linear kernel model to this data. I've kept it kind of general here, so I'll share a link later where you can sort of copy these code blocks as well. In principle, this should work for any number of environments and managements, theoretically. In practice, maybe it becomes hard to fit. So yeah, we have the function, which again takes order and kappa. And just to quickly show, we have, again, a bit of code to compute the covariance matrix, derivatives with respect to the variances, and then the derivative with respect to the correlations. In our case, we only have 2 managements, so this would be a single correlation. We return those. We specify the initial values in the parameter types and constraints, and then we can fit the model, well, similarly to how we did in the first example, except that we do it for the management by environment vector here. So we construct this Kronecker product that I mentioned. We actually construct that within the function, which means that we only need a single factor here. Fit it, and then once it converges, we'll look at the variance components. And oh wait, my screen is a bit too narrow. There we go. So note that you don't get any kind of description here. So if you want to know which variance component, well, is which parameter, then you do need to, let's say, think back about how you specified it. So what I did here is the variances come first. Well, we only have 2 managements, so we're going to have variance for management 1, variance for management 2, and then at the end we get the correlation between the 2 managements. So what do we get? Well, we get variances that are fairly similar, and we get a correlation between management 1 and management 2 that's 0.7, so quite high indeed, which also matches what we saw in the plots. So yeah, that's the how you would fit the model with a single variance and a linear kernel. The second option within the idea of the linear kernel is to use multiple variances. So the formulation in mathematically looks slightly different. We used to just have a covariance matrix for the management and then the linear kernel and the kinship. Now what we do is we actually estimate a unstructured correlation matrix for the managements. We have the linear kernel, which, if you remember, is also essentially correlation matrix. We then first take the Kronecker product of those 2, and then we kind of add the variances for all E by M combinations on top of that. And then once we've done that, we multiply with the kinship. So our vector kappa is going to be a little bit longer. We now have 4 variances. The variance for, let's say, management 1, environment 1, management 1, environment 2, second management, first environment, and the second management and the second environment. This is also the way that I've specified it in the code. And if you want to use that code directly, then it is important to order your data correctly, because we're putting the management on the left side of the Kronecker product and the environments on the right side. That means that let's say in your data, so in your data frame, the environments need to be nested within management. So we first get all the environments for the first management, and then in the rows below, we get all of the environments for the second management. If that's flipped around, then, I mean, that would be fine as well, but you would have to flip those matrices in the code in this external variance function as well. Because again, ASReml has no idea which parameters relate to which factor necessarily. So yeah, just to clarify, I mean, SS transpose is simply, well, S is a column vector which contains the standard deviations. So that'll give us a big matrix with the variances on the diagonal and the products of the standard deviations on the off diagonal, which we need to compute the covariance matrix here. Like I mentioned before, we are doing this also means that we get a unique rate of shrinkage for each combination, which might be nice from a prediction point of view. I won't go into detail, on how the covariance matrix looks and what the derivatives look like. I wrote a sort of blog post where I included some more information and more examples. So you can look at that later as well if you want some more info. Graphically, it looks like this. Like I mentioned, we have an unstructured correlation matrix for the managements, linear kernel for the environments. We first, take the Kronecker product of those to kind of expand it. Then we put the variances on top, and finally we multiply with the kinship for the genotypes. So I can again just quickly show that in R. I won't go through the entire variance function again. It's similar, except that it has multiple variances now, which also means that we have more derivatives. So we'll specify the variance function, then we'll get the initial values, types, and constraints, and then we'll fit the model. And then when we look at the variance components, we'll see that we now have 9 variance components plus the residual. The last one is going to be the correlation between the two managements, and the first 8 are going to be the variances for the 2 times 4 is 8 management by environment combinations. Again, they don't include a label, but what you can do is you can just look at the levels of the management environment factor in your data, and then those match, or those are in the same order as these estimates. So 0.26 would be the variance for the rain-fed trial at the bowl 12 environment, so to speak. And 0.94 would be for the last one. And we still have, we have some differences in variances, and we still have a relatively high correlation between the managements, so that's good. Then, those were the linear kernel models, and now we can move on to the nonlinear kernel models. Why would you want that? We want that because, let's say, a kind of drawback of the linear kernel is that the G by E pattern is completely fixed, right? Because remember that I mentioned that this matrix C, or this linear kernel, is essentially correlation matrix. That means that we don't leave any kind of estimation to do in the model. This is just what you're going to get, and that's it. So there's no flexibility to make it fit the data a little bit better. You're really trusting the environmental covariables, and if those are for some reason not accurately describing the G by E, you'll get a bad fit. So a nonlinear kernel introduces just a little bit of flexibility to make the model fit the data a little bit better at the cost of a single parameter. And it's going to be a single parameter regardless of if we have 3 environments or 20, as we'll see in the next few slides. So what do we need to get this nonlinear kernel? First of all, it's based on a distance matrix. I call it nonlinear kernel. In this case, what I'll show here is a kernel that uses a distance matrix containing squared Euclidean distances between environments. How do we compute that? Well, the distance between environment I and j would be, let's say, the sum of the squared differences for all of the environmental covariables for environment I and environment j divided by the number of covariables, where W is the same matrix, except we scale it across the or along the rows now. If you use this kind of distance matrix, I think it's often referred to as a Gaussian kernel. You can also take normal Euclidean distances, and then you would end up with, I think, what people call an exponential kernel. But for now, we'll focus on the Gaussian nonlinear kernel. This is what the distance matrix would then look like. It's symmetric, of course, and on the diagonal, it's going to have zeros because the distance between, an environment and itself is obviously going to be 0. And then comes the nonlinear part, which is simply a transformation to a correlation matrix using a parameter that is often called the bandwidth. So what we do is we just take e to the power minus h times the distance matrix, and that gives us our correlation matrix that we then use in the model. And just to see the effect of these bandwidths, we've got a graph here with on the y-axis the correlation that we end up with in our final matrix. On the x-axis, we have the bandwidth, which is strictly positive, so from 0 to infinity. And in the different colors, we have the different squared Euclidean distances between, let's say, a pair of environments. So what you see is if this distance is small, that means that the environments are very similar. So for any bandwidth value, we end up with a correlation that's close to 1. If we do have a large distance, then that means that the environments are dissimilar, which means that even for small bandwidth values, the final correlation very quickly gets pushed towards 0. And of course, for intermediate values, it's somewhere in between. So one drawback or one, let's say, restriction on using this kind of model, that you can only end up with positive correlations, which in my experience is fine. I don't think negative G/E correlations are super common, but just keep that in mind that you won't be able to model those using this kernel. So we now want to combine those again in a mixed model, which means that we have, again, the unstructured model for the managements and a nonlinear kernel for the environments. And this H, previously for the linear kernel, we didn't have to estimate anything here. Now we have D, which is given the environmental covariables, and we've got H, which is something that we actually need to estimate using ASReml. We have the same two options, single variance for all environments within each management or unique variances for all of the combinations. So here we have the single variance version. This expression here looks very similar to the linear kernel model, except for the fact that we've replaced the C that was here with, e to the power minus HD. And we've added the bandwidth to our factor kappa as an extra parameter to estimate. And like I said, the way that these are all computed, the covariance matrix and derivatives is very similar, except for the fact that we replace C by D, or e to the power minus HD. And of course, we end up with an extra derivative because we have an extra parameter, so we need the derivative with respect to this parameter as well. Graphically, it also looks the exact same, except for the fact that this is now a nonlinear kernel instead of a linear one. So I can again show in R how we would fit that. I've chosen to get the variances first in my kappa, so to speak. Then we get the correlations, in this case only one, because we have two managements, and the final element in kappa is going to be the bandwidth. So we'll specify that function. We will set the initial values, the types, and the constraints. And you can see that the last one is the bandwidth. So we just use 0.1 as well. We treat it as a variance because it has to be positive. So essentially it should follow the same rules as a variance. And we set the constraint here as well. Then we fit it. So the call to ASReml looks basically the same, except that it's going to estimate this bandwidth now as well. There we go. Then if we look at the variance components, we have variance for management 1, the variance for management 2, and the correlation between management 1 and 2, and then the bandwidth. So you see that the variances are more or less the same as what we saw before. Correlation is also still quite high, around 0.75, and we get a bandwidth of 0.18. And we can actually use that bandwidth to compute the correlation matrix that ASReml kind of made internally. Look at the distance matrix. Well, makes sense. We've got zeros on the diagonal, positive numbers on the off diagonal, because the distances have to be positive, of course. Then if we take e to the power minus the final variance components, which is the bandwidth, multiply that with the distance matrix, and that should give us the correlation scale, let's say nonlinear transformation of D. We can then compare that to the linear kernel that we used before, and then you see that, the flexibility is quite useful, because I'll show later that for the drops data, the nonlinear kernel worked best by far. Because, these are very different, right? We've got negative correlations, minus 0.22 here between guide 12 and card 12. And if we let ASReml use this bandwidth to make the kernel fit the data a little bit better, we actually end up with a correlation of 0.6. Now, that doesn't mean that this is perfect, but it means that this one's probably closer to the, the true correlation than what we had here. So yeah, that's the single variance kernel, nonlinear kernel. We can do again the exact same thing for the for the multiple variance version. Again, this is very similar to the multivariance linear kernel, except that we've again replaced C by e to the power minus HD. We've got the extra parameter, and again, what we do is we estimate H. H gives us the nonlinear kernel here in green. We multiply that with the unstructured model for the managements. To expand this thing here, we add the variances on top for all of the environment by management combinations, and then we finally multiply with the kinship for the genotypes. Here I did write them out again, just for reference. If you want to look back at it later, this is essentially what happens, right? So this SS transpose will give us this big matrix with the products of the standard deviations and variances. And then here we have the unstructured correlation matrix for the managements and the nonlinear kernel for the environments where we estimate the bandwidth. If you multiply all of that together, you get the expression for the full covariance matrix, which again is one of the things that should be returned by our external variance function. One of the other things is the derivative with respect to the bandwidth. That one's actually fairly easy as well. You just use the rule for the derivative of some exponential function, and then you end up with this. So I'll show that one in R as well. Yeah, so the way I've done it here is I first take all of the variances. I've used trait here, but I'll show later that you can use this for traits as well, multiple traits. Just imagine this as management. So we would have the variance for the first management, first environment, variance for the second environment within the first management, all the way up to the variance for the last environment in the last management or trait, which in our case would just be the second management. Then we get the correlations, which there would only be one correlation again. And then finally, again, we get the bandwidth. So we specify that function. Again, this top part is responsible for computing the covariance matrix. Here we get the derivatives with respect to all of the variances. Here we get the derivatives with respect to the correlations. And then the last thing is the derivative with respect to the bandwidth, which is already in the correct order. So that's nice. We return those, and that should allow ASReml to fit the model. We set the initial values again. So, we just use the number of management and environments because we will have a variance for each of them, each of those unique combinations, types, constraints, and then we'll fit the model again. And then if we look at the variance components, we indeed get 11 in total, 10 if we ignore the residual variance. We will have 8 variances for the 2 times 4 combinations. We'll have a correlation between management 1 and management 2, which is again around 0.75, so that's good. And we have the bandwidth, which is also very similar to what we found with the single variance models, around 0.18. So yeah, that's essentially how you would fit the multivariance Gaussian kernel, nonlinear kernel, using this external variance function. Then a word on how you would use this for multiple trait data. Well, it's actually quite easy. The variance functions are exactly the same. So later I'll again share a link to this kind of blog post where you can copy these code blocks. You don't have to change anything there. You can use those as well for multiple trait models. The only difference is that you do need to format your data a little bit differently in a specific way, and you also need an extra option in the ASReml call. So the way that you would format your data is essentially in a long format. So maybe you have a different column for grain yield and a different column for, let's say, flowering time. If you want to fit it using this own function, as far as I know, you have to put that in a long format. So you simply take all of the rows for grain yield and stack those on top of all of the rows for flowering time, for example. Then if you do that, you also need to specify an extra function or argument in the ASReml call, which is the ASMV argument. I honestly have no idea what it stands for, but essentially it lets ASReml know that there are fewer units than rows in your data frame. Because if you stack those traits on top of each other, let's say that we've got 100 genotypes, 10 trials, and 2 traits, we would end up with a data frame with 2,000 rows. And if you don't specify this ASMV argument, ASReml is going to think that you also have 2,000 units, so 2,000 actual plots. But that's not true, of course, because we just have 2 traits that were measured on the same plot. And if you try that without ASMV, you'll well, it'll start giving you warnings or errors actually about the number of units not matching the number of data records. Yeah, because I mean, we want to include an unstructured model for the residual covariances of the traits and then multiply that with a diagonal model for the actual plots, so to speak. But that's all there's to it. So yeah, it should be fairly easy to use for multiple trait data as well. Then a few quick results. This is also using the drops data, the full data set. So it has 2 management, rain-fed and irrigated, 14 environments, 246 genotypes and environmental covariables from weather stations in those locations. The non-checked genotypes, because this is within this kind of sparse testing setting. So we have a number of checked genotypes that are evaluated in all 14 environments, and the non-checked genotypes are tested in 2 out of 14 environments. And so what you see is we have the linear kernel models in this kind of orange and green, and then red and dark green are the non-linear kernel models. And the black one is the main effects model, so it completely ignores G by E, and the blue ones are the factor analytic models. So what you see is that, up to about, well, let's say 40 checks, the models using this nonlinear kernel slightly outperform the FA1 model, and the higher order factor analytic models drop off, let's say, even more strongly. But if you have a lot of connectivity, so if you've got, if you're getting close to a nicely balanced data set, then the factor analytic models actually do slightly better, which is also, I mean, makes sense, because those will be able to fit the true G by E probably better from the phenotypic data. That was for the rain-fed management. This is for the watered environment management, but we see more or less the same thing. Yeah. If we then look at errors, we see, well, something similar. We also see that having multiple variances in this case results in slightly lower errors, again, up to about 40 checks. Then I also looked at a small subset of the genomes to fields data, includes 2 traits, 4 environments, 339 genotypes, and actually environmental covariables from an open source database, NASA Power, it uses satellites to measure environmental covariables. So you can get that for any location on the planet, which is pretty cool. Here, non-checked genotypes are tested in 1 environment, and there's a little bit more G by E here. So you see the difference with the main effects model is bigger, and also these kernel models up to about 50 checks, let's say, slightly outperform the factor analytic models. After that, you're better off fitting the factor analytic versions. So then a word on code availability. I made a kind of blog post that has well, a more in-depth description of all of the models, the covariance matrices and derivatives for let's say a simple 2 management, 2 environments example. It also has code blocks that you can just copy and paste to use it with your own data. I also made a very simple R package, decided to call it corn fruit, but it just makes it a little bit easier. So instead of having to copy this big code block, you simply have 4 functions corresponding to the 4 models that I talked about today. You can just read in any kind of file for your distance matrix. That will return the correct variance function, set the initial values, and then you can reference that function to fit the model. So that's available on GitHub if you want to try it out. So with that, thanks. And yeah, I mean, if there's any questions, I'll be happy to try and answer those. If we don't get to it, you can also just send me a message or an email later if you want, and I'll see if I can answer those questions. So thanks again, and yeah, let's see if there's questions.
Yeah, we've got a few in the chat. There's also a lot of people asking for if a webinar is going to be recorded and sent out. So I think a lot of people enjoyed that one. It seems. I'm keen to watch it again. We've got one question from João Gabriel from Klabin in Brazil. Great lecture. Do you often use some type of phenotype correction, blues, digressed blurps before fitting a genomic by environomic and management models?
Yeah, so you mean, I guess, a sort of 2-stage approach. Yeah, I think that's what drops is based on as well. So drops also use, let's say, first stage analysis for the single individual trials to get the blues, and then those blues can be fed, possibly with weights into a second stage model, which models a G by E. So yeah, I think that's a fairly common approach to model G by E. Yeah.
We have a follow-up from Zhao as well. Oh, I've lost it. Give me 1 second. Sorry. It also says, I think we might have covered that on some of your last slides. This question came in quite early. Can you share how much improvement in predictive ability you got by adding environmental covariates in your analysis?
Yeah, so for the drops data, well, the drops data doesn't have a huge amount G of G by E, so the differences are quite small. We're talking about like 0.03, 0.04, and it also again depends on how many checks you have, so the connectivity between the environments. For the errors, yeah, it's sort of similar, I guess. I mean, you could use the main effects model as a sort of reference level, I guess. So here it looks like you do have a sort of decent improvement if you look at how well the main effects model does. For the other data set, the improvements are a bit larger, right? Because I think there's more G by E in this data set actually. So yeah, how much it's going to improve depends, of course, on how well the environmental covariables say something about the G by E. And I think in general, it depends on how much G by E there is to begin with. So yeah.
Great, thank you. We've got a question from Tolera Keno. If I want to determine which environmental variable has the greatest influence on the expression of a trait, is there a way to do that?
Yeah, that's a very good question because I think that's actually quite complicated because there's here I just showed these kernels as well. We have them, but there's a lot of stuff that goes into getting those, well, let's say getting the environmental covariables to get your kernels. Um, I've actually, so using this satellite data, you get a whole bunch of stuff, and I just subsetted it to variables related to temperature, radiation, and water availability. But I didn't necessarily do any kind of subset selection. So yeah, it's a very good question. I think it's quite a hard thing to do as well, because indeed, if you just throw in all of your covariables, there's a good chance there's going to be a lot of noise in there, which makes it so that your kernels don't really match the actual G by E. So I don't really have a very good solution for that right now. Yeah, I think you would have to probably do some sort of subset selection using regression or something like that. But yeah, it's a very good question. Yeah.
Thank you. Got a question from Juan Jimenez. Killian, do you assume all genotype, environment, and management combinations are observed?
Sorry, what was that?
Do you assume all genotype, environment, and management combinations are observed?
Well, in this case, for the sparse testing setting, of course, there are missing, go back to the start, there are missing combinations. What I did here, and that's also characteristic of this drops data and some other data sets that I've looked at as well, is that both managements are actually available in every environment. So it's simply a low and high nitrogen, irrigated versus non-irrigated, and those are both tested in all environments. Of course, that doesn't necessarily have to be the case, which would complicate things. But it's not necessary to have, let's say, all genotype by environment management combinations, because that's the idea of the sparse testing. So no, that's not necessarily assumption, but I think it would be a bit flexible, but it would probably make it harder if there are larger gaps. So yeah, that's true.
Fantastic. Question from Suresh Antre. How to decide fixed and random effecting model when we want to have breeding values of the parents from hybrid data by considering G by E by M?
So I assume you mean whether you want to model the genotypes as fixed or random. Well, I mean, if you want to use the kinship for genomic prediction, you're going to have to fit it as random anyway, because you want to model it using a covariance structure, and that's only possible for random effects. So I mean, for this first stage analysis, I guess you would use them fixed, obviously, to get the blues. But if you want to do some kind of genomic prediction, I think you have to fit them random.
We've got a question from Daniel Tolhurst. Nice talk. I missed what you were correlating in terms of the accuracies. Can you please re-explain the first results plot?
Yes, so there is, yep. Let's say we've got Pearson correlation, so that's the correlation between the blobs. So only the random effects, not the fixed effects for the environments added. So it's the correlation between the blobs from the mixed model and the centered phenotypic data of, let's say, the test set in that environment. So the missing G by E combinations. In this case, you could include the fixed effects as well, of course, which would simply be the average of, but all of your predictions are going to get the same fixed effect added. So that's the Pearson correlation. RMSE is also using the blobs from the random effect as well as the centered phenotypes for the test set, but it's just a root mean squared error. Yeah.
Perfect. We've got a question from Dong Lee. What are the advantages of the model you showed over the joint regression analysis, like FW regression, in terms of prediction? Thanks.
Yeah, that's a good question. I didn't actually so far look at the sort of random regression kinds of things. So yeah, I think there's different ways of modeling or including these environmental covariables, and I mean, what I've seen in let's say other things that I've done in the past year and a half here during my PhD is that I think, to be honest, oftentimes a lot of models end up with more or less the same performance, right? There's multiple ways to do it. I don't know if I would necessarily expect huge differences between deciding to do some kind of regression or a model that includes them in a covariance structure. I mean, technically, of course, using a kind of kinship for the environments is kind of analogous to doing a ridge regression on the environmental covariables as well, just like gblob is essentially ridge regression on the markers. So yeah, in that sense, I think they are fairly similar, probably, but I'm not 100% sure.
Fantastic, and we've got quite a lot of questions coming in, lots of different things, but we'll make this the last one. If we haven't come to your question, then we will we'll send out all the questions and answers later when we send out the recording of the presentation as well. So yeah, please just keep an eye out for them. So we've got hello, Eduardo Capa from Buenos Aires. What is the difference between the Kronecker product parameterization of sigma and score env, one variance and one correlation between the environment, and K based on pedigree or markers, and the reaction norm model proposed by Jacquin et al., which uses the Hadamard product parameterization for sigma underscore env and K?
Yeah, that's a very good question as well. I think what indeed these reaction norm models by Harkin, they often use a Hadamard product because they, I think, often use phenomics data to construct these matrices. And what they then do is they have, let's say, measurements, so phenomics measurements on all of the G by E combinations. And that allows you to construct a kernel that's, let's say, already the correct size. So it already has the size corresponding to all of the genotype by environment combinations. And then you would simply expand your kinship as well using design matrices. And then you simply take the Hadamard product between those. But actually, if you use environmental covariables to get a kinship of the environments, you take the Kronecker product with the kinship, that's actually identical to expanding both of those kernels, kinship and the kernel, with the corresponding design matrices. So expand those and then take the Hadamard product of those, you'll end up with the exact same thing. I think there's also a paper on that, which I might be able to forward after the meeting, that shows that if the data is ordered correctly, you end up with the exact same model. So that's, yeah, for a large number of cases, if you don't have data on every genotype by environment combination, every plot level thing, so to speak, then using a Hadamard product or with the design matrices or the Kronecker product is going to give you the exact same model, actually. So yeah, that's a good question as well, because I think a lot of people think they are very different, but I think they're actually very, very similar, if not identical, in a lot of cases.
Fantastic, thank you. Well, we'll end it there. As I said, if we haven't come to your question, then we'll send out a full list of the question and answers after, along with a recording of the webinar. So thanks again for a wonderful talk, Killian. That was brilliant. No problem, anytime. And thank you everyone else for joining us. Hopefully see you at the next one.